All right. So hello everyone for joining us on the TD3 Implementation Week. And unfortunately, this week is just me and Roslyn. Regardlessly, we're very excited to show you what we got. TD3 is a very interesting algorithm, and we already see a lot of improvement towards DDPG empirically in a couple of the environments we've tested, but it's not as good as the author's original implementation. So that's something that I want to look into next week. So to start off, let's take a look at the performance. I believe I run the experiments on Walker and maybe mountain car? No, not mountain car. What's the other one? Humanoid? Not humanoid. Pendulum? Yes, pendulum. Okay. So let's take a look at here. If you watch closely, you'll realize that TD3 is one of the best performing agents. It's if you look at its training compared to DDPG, DDPG suffers a lot more variance, and its episode rewards just its average stays around 200-ish, but with TD3, the average rewards stays around 600 to 700, which is not great because with Hopper, the best performing agent that we had could go up to 1500 or something like that, very high. Here we see SAC is still Soft Actor Critic is still the best performing agent over here, but we already see TD3 as a significant improvement over DDPG. And this kind of thing also kind of happens with Pendulum, although the DDPG is not as advantageous as in the previous environments. Here, DDPG and TD3 achieve similar results. And lastly, we have Walker. Let's take a look. Here we have TD3 performs also about twice or three times as better as DDPG. If you look at the performance, but overall, yeah, it's not as great as it could be. And I ran the algorithm using the author's original implementation. And with Hopper, at least, the author's original implementation is able to reach something very high, like 1800 reward. So that is much, much better than what I have over here. But it will be very interesting to see what the author is doing differently.
Is it even better than Soft Actor Critic?
Yes, I believe so. But even with the PPO2, with all the code level optimizations, it's performing better than Soft Actor Critic. By the way, I almost feel like we really should have done the soft actor critic implementation after DDPG and TD3 because it seems to me that the soft actor critic has a lot of components from TD3 as well. Like for example, the minimum of the 2Q value. I think that's very similar.
Yes.
Right, so let's take a look at the implementation that I did in contrast with the paper. Is this the paper? No. Okay. TD3 paper. I used the diff checker to just show the difference between DDPG and TD3. And remember, there are essentially three components to this. Let's see. Okay, perhaps it would be helpful if I just use my own slides. That'll be easier to extract information. Right. Okay. So I guess a couple things. The first thing is the clipped Q-learning. Essentially, they also ask you to create target Q networks as well as target actors. So that's the first thing that needs to be changed. I'll go back to these later. So by the way, on the left is DDPG and on the right is TD3. So right off the bat, we created two Q networks as well as their corresponding target network. In addition, we also create target actor as well. So that's also something different. And the other thing that is different is we have a policy noise, which is for the third technique, the target policy smoothing regularization. Remember, it's the idea that you add a little noise to the action being generated to when you do the training. However, you still have an exploration noise that is a little different than the policy smoothing noise. So over a TD3, you have two types of noise. And I use the hyperparameters supplied by the original author. And for action noise, I believe he just used 0.1, and for policy noise, he uses something like 0.2 or something
Yes,
like that.
that is it. 0.2.
Yeah, which I haven't included here. Yeah, to further elaborate, the policy noise is essentially multiplied by a randomly generated Gaussian noise. The other thing that is required to do is I deleted the 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 explanation noise annealing. So as you can see over here, I don't do that anymore, and that is the same as the original author's implementation. And in a way, I almost feel like this could be the reason why our DDPG was performing so badly, because maybe the noise shouldn't be annealed at all. But
I do not think so, because in my version I do not use any annealing method whatsoever, but it's basically the same result. So
oh, okay, maybe it doesn't make a difference after all, I suppose. But then, essentially, after your learning start, which we set to be 5,000 time steps, before which you're essentially populating the experience replay by using the inv.actionspace.sample. And then after that, so this is something that is different, right? Here in the DDPG, you're essentially updating the Q network, updating the target. But on the other hand, on the TD3 side, you're just updating the Q network. You're updating the critics only. And only after a policy, after a certain frequency, then you do the delayed update on the actor as well as updating the target network. So that's essentially the tween delayed. This might be a little messy, but let me show you the actual code. It might make more sense. So if you take a look at TD3 no noise annealing, essentially you update the Q networks over here, and then after the after a certain policy updating frequency, which in this case it's about 2. That's a hyperparameter extracted from the author's original implementation. And then you update the actors, and then you also update the target network by copying the target actors voids, copying the weights from the original policy from the main actor or Q function to the target actor or policy. I said that right? Anyway, and that's it. That's the TD3, and it already shows a lot of improvements. And I did run with the author's original implementation, and his version is better. So that's something that I'll go and investigate and try to figure out what's wrong. And I want to stress a little bit on how the author handles the third technique, which is the target noise. target policy smoothing, or how he calls that technique, target policy smoothing regularization. So this is the implementation. So first of all, you clip a noise. You generate a noise by using the policy noise, and then you clip it to a certain range.
Okay,
And
I have a question here.
yes.
Actually, I need to look on the paper, but I do not really see the need to clip a noise. I think you should first sample the noise, add it to the next state actions, then clip the next state actions. Because
If
we
you
already know the range of the noise,
So if you look at the noise, if you look at this part of my screen right here, y is
okay.
equal to, yeah, you see the epsilon is clipped first before it's added to the policy, before it's added to the generated action. I mean, what you said could work. Actually, it wouldn't work, right? Because then your action could be fairly arbitrary, and then how you would set up the clipping coefficient is non-trivial.
I don't quite get the intuition about clipping the epsilon noise at this step. So
I don't
I
know. I
don't
feel
know.
like if we use this again, using the circle as an analogy, I think it's essentially saying when you expand it like that. So this is adding. So imagine if you're on a real line, on a real value line, right? And this is a real line. Let's
Mhm.
And maybe these are the two actions you generated. And the idea of the target smoothing is you expand their range, right? So that they may overlap a significant portion. So that they may look something like this. And they have a higher chance of being considered as the same action. And the clipping, I think, it's essentially saying we want to do this. Oops. That's pretty terrible, but you know what I mean?
Okay, we want them to be similar to a certain degree, but not too much either. That's
I suppose they don't want it to extend too much, right?
okay. Makes
So,
sense.
in other words, it doesn't extend over here.
This could. Okay.
Yeah.
Makes sense.
Yeah, I really hope I don't have corona because I've been staying at home for almost 3 weeks.
Hmm.
Let's hope that's just normal laugh. Sorry, normal cough or something.
Okay, I see.
Yeah, but it makes sense, right? Over here. Oh, yeah, it makes perfect sense because you see the net results over here. They don't extend anymore. They don't
Hmm.
extend this part, and they have more part that are in common.
Oh, nice.
Yeah, so I think it indeed helps the actions to be similar to be considered the same. So yeah, I think thanks for bringing it up. I think it's it's great for me to get that intuition as well. Before I wasn't thinking that much about that, I guess. But yeah, that's about for TD3, and I'm really looking forward to just porting over the author's implementation, change all the variable names, and make it look exactly like that. And I do a
So
difference at the time. Hmm?
actually, I did have one more.
Question? Yeah, go ahead.
Not really a question, but I need to. Could you bring the paper, the algorithm, please?
Yes.
The TD3 one.
You mean the
In the paper or in from your slides.
uh,
The second where they update the target network.
over here?
Uh, okay, I see. I get that that's what the author does, but why are the target networks updated every D? Like
So,
if a T mod D instead of, especially for the value function, I do not really see why it's under the scope of the actor update, the policy update.
So the target network is basically saying don't update the target network until the critics converge or the actor converge, right?
Mm.
Well, actually, the actor is not even updated. So yeah, the actor is only updated tmod n. It's really just saying the don't update the target network until the critics have one more time step to train and converge, right?
But in the end, both are updated, right? I think this part does not really. I understand we want to update the actor
Mm-hmm.
with more precise queue function, right?
Right.
That's the idea behind delaying the updates between both components.
Mm-hmm.
But why we also need to update the target networks with respect to that system? I do
Because
not really
because
agree.
because when you do when you're generating the data or things like that, you're using the target network to generate the actions as well as using the uh, target network to generate
The noise and so on. So, for example, since we want a more precise critique, I will say that intuitively, at least the updates of the Q value function target network should be outside the scope of like the T mod D, if it makes any sense, because
well, what should be outside of the TMLD?
the phi dash receives yes, the last line basically. Oh no, the theta I dash is updates,
Okay. Um.
because if we delay the update of the targets, how are we sure we are instead not making it worse for the Q value themselves to learn?
Well, I
It's a
think
detail.
I think delaying the target network um, um, is essentially saying when you generate a target for doing the Q loss, which is over here, you're saying let this part r plus gamma times minimum of those two Q values. They want the Q values over here to be as stable as possible before it's changed, right?
So they even delayed further. I see.
I think so. Yeah.
Well, with regard to that, I remember the author said, or at least they assumed, they claimed, or they assumed that for a bigger update delay, we would have better results. I'm not mistaken, somewhere in the paper.
What delay you will have better results?
The on the line, if a T mod D, then the D,
Yes.
they claim for a bigger D, they will have a better result, but there is a cost in computation. Or
I would imagine so, but yeah, I think that would be interesting to implement as well.
or actually, I already run some experiments.
Yeah, do you want to show us?
It turns out it's not that helpful.
Okay, let's take a look.
So
So the update delay. So what's the best performing one? About
the best performing
three?
one is still the one corresponding to update delay 2.
Ah, that's interesting.
It's the
So,
default, right?
so maybe too much delay is not that helpful. But no, you're So there's a reason why it performs worse, right? Because you really should. The x-axis is the number of global step goes, but if you want to do this comparison, you really should be the x-axis should be the number of times the actor is updated,
The
right?
number of times the actor is updated should be, hopefully it's logged, hopefully, and it's not.
Because it's the same thing with the DQN compared to PPO, right? The reason why PPO with the same number of global steps is not performing as well as DQN is simply because it doesn't have that many updates. When you do update delay as many as that, then the agent doesn't get a lot of chances to learn. That's why it takes long. That's what he means by the computational time is going to be longer, right?
Okay, so you will have to sample Like, for example, 2 million steps before reaching a similar performance.
So, in other words, if you look at the code, that would mean your x-axis should be how many times this is called. Does that make
Mm.
sense?
Yes, yes, yes.
Yeah. So, or at the very least, so instead of saying while global step is less than total time steps, you say while global step is less than um, something like while the actor has not been updated for uh, 20,000 times or something like that.
Okay. I kind of get the idea now.
Yeah. So I think by using, hold on. So I think by using your demonstration, then the graph, the diagram with the update delay equals to 10. The number of global steps really should be 10 times as many, right?
Yes. Okay. That's quite an unfair comparison indeed.
Yes, indeed, because it doesn't get that many chances to learn. But with Walker D, it's performing pretty well, right? With the update delay.
In that case, yes, I guess. But
That's
that's really the smooth curves only.
right.
The
That's interesting. Yeah,
actually
so
environment still
it
quite
helps.
hard.
Yeah, so it helps with episode reward, but it still has a lot of variance. So I would be very interested in knowing what's the author's magic in making it look so smooth, I suppose.
Yes, indeed. I am really curious about it too.
Yeah. So I think that'll be very interesting to investigate next week.
Maybe what layer size do you use?
Nothing too fancy. Just
In the paper, say they use 200 times 300.
oh,
So
definitely I
maybe
wasn't using that. So that may be a
that.
reason.
Mhm.
So maybe you don't have to look at a paper, but you can just look at a TD3's implementation. I really like how the author include a copy of their DDPG implementation because in that case I can sort of copy it, for our use, I suppose.
Oh, nice.
Yeah, what do they use? They use 256, a lot of 256. And
The learning rates are also different from the paper, it seems.
where is the
The
learning
paper,
rate?
it's LR, I think. LR, line 83.
Right. Yeah, it's a much more aggressive learning rate.
Oh, smaller, you mean?
Wait, is it smaller than ours?
Yes, I think.
Really?
We're using 1 exponential minus 3, right? 0.001.
No, we're using 7e minus 4. So that's
Okay.
7 times more than what they're using?
Despite that, the variance is quite high.
Sorry, not even 7 times, but more like 2 times. Yeah, there's a lot of things to, investigate into this. But I think it should be fairly straightforward to understand everything. Yeah, they included DDPG as well, which means it should be fairly easy for us to reproduce the results and stuff like that.
Okay, wait. I think there might be a little trick, little trap.
Hmm?
My computer does not follow. They say in a figure 5 in the paper, uh,
I'll look at your screen.
yep, but curves are smoothed uniformly for visual clarity,
Uh huh.
obviously.
Right.
So this may be another trick that actually maybe it's not that smooth in the author's work.
Oh, I don't know. When I experimented with Hopper, it was very smooth. Like the
Really?
you see like one 1500, 1500, 1500. You see something like that. But with my implementation, you see like 1500, 200, 1500, 1500, 200. There is very, very smooth. So that
Okay.
another reason for my excitement to see what they're doing differently.
Also, the evaluation itself might be deterministic without the noise applied to the actions.
I
Or
see.
is it?
Uh, I am not sure, but that, to be frank, that's also not something that I'm very interested in. Like, it's cool, but I feel like during the training, you essentially have the you evaluation is more like something like a cherry on top, but it's not important to me at least.
My intuition would be that the noise we apply to the action every time could cause the variance because there is so much little like leeway between an optimal action and a suboptimal one. So
Right. So, based on my observation, by using their implementation, it doesn't make it. The evaluation score is not so different from just a training score. It's all 1500, 1500 once it starts to converge. It's very, very good.
okay, maybe it's not that important at all.
Yeah, that's how I feel.
So what's the name of the repository again?
It's posted in a paper, but if you want, just search TD3. Just search TD3 PyTorch or something like that. That will be definitely the first thing that pops up.
I see.
See? Yeah, and their code. I'm so glad that their code is simple. It's not something like yet another OpenAI baselines to read. Oh, and also interestingly, did you notice they use Relu?
Mm-hmm.
Yeah, so that's
They do.
something to be changed as well.
What are you using?
Oh,
10.
sorry, I am using Relu. Never mind. So,
There isn't that much choice when it comes to activation.
oh, actually, sorry. Let me see real quick. TD3. Do they use 10 at all? Yes, they do.
10 is for the last layer of the policy. You
Yes.
scratch it between -1 and 1.
Right,
Probably.
right. So I also did that. So that should be fine. But what about for the critic? Critic is always Relu. Yeah, I did the same, I suppose. Okay. Yeah. But yeah, definitely something to investigate. See, he does the same thing as I did over here.
That's
Just copy
exactly.
and paste it instead of having like another function. In my opinion, would be pretty redundant. Just say soft update versus hard update. Just kind of there it is. But that's maybe beyond the point. Okay, yeah. All right. Something to discuss next week. Oh, right. Sorry. Let me introduce a comparison that I did. So here you see we have a TD3 continuous action and TD3 no noise annealing. No noise annealing meaning no policy noise annealing. Sorry, no action noise, or sorry, no exploration noise annealing. So I'm actually kind of interesting to see which one is performing better. So it would appear that with policy noise annealing, it is performing better in Hopper. Does that results extend in Walker? Let me see. It doesn't. So with the noise annealing, it's maybe kind of random. It doesn't really matter, maybe. But yeah, that's about as much as I have for this week, and I want to kind of talk about an interesting bug that I had. So the reason why DDPG's comprehensive benchmark was delayed so much was because DDPG took a really long time to run. So if you look over here, when we run the DDPG on our server, it takes 5 days and 21 hours, 41 minutes to finish. That's a really long time. And what's the reason? So I posted an issue in Wait and Bias's client. It turns out this is my machine with a very good hardware, state-of-the-art hardware, and a very good disk. As you can see, the majority of the time being spent is the algorithm itself. However, in our big server, you see that the writer, which just adds scalar or adds summary, takes a significant amount of time, and it's very concerning. And that's one of the major reasons why this is taking 5 days. And with the further investigation suggests that it was this thing, PostGIS fsync file sync, that's causing. That's what mostly costs the time. In the Python implementation, it's just something like os.filesync fsync. That's costing most of the execution time. So it wasn't a difference between CPU versus GPU. It was mostly with the writer that's costing us time. And one of their contributor responded to me that currently it seems one of the only way to sort of help with the problem is to setting up a rate limits, which limits the number of writing per second. If we set it to 2, then there's no performance overhead. However, that solution is not really optimal because then you're losing a lot of potential writing from the TensorBoard writer. So what I did was I use a shared memory folder because I figure, if the file sync is causing this to slow down, why don't I just use the memory itself, which I just use a dev shm folder, then everything just so smoothly. There's no overhead anymore. So we go from 5 days, 21 hours to 7 hours. So
It's quite an improvement, indeed.
yeah, that's like something like crazy. That's like a 10 to 15 times speed up. But yeah, I was very happy about this. The other
I am
thing,
curious on why I did not notice such a time clock.
uh, I mean, it's kind of hard to find. It took a lot of time to do all those things that I did. I have to profile everything, and the profile isn't as simple as what I posted over there. It's there are different.
It's a hopper, right?
Yeah, there are also different ways to do the. So I think if your server is using a non SSD disk, I think this is especially worse because the file sync would take much longer.
I am pretty sure the servers I used are all HDD,
Okay, yeah,
not SSD.
that would
But
be interesting. I don't know.
this one, for example, takes only 4 hours. So, although it's DDPG. Maybe the logging frequency is too high.
I'm not so sure. You're more than welcome to do the profile yourself. I believe I included part of that in the GitHub issue. So if you run something like, oh, I didn't. It's just a C profile.
Mm-hmm. Yeah, sure.
But yeah, so right now, I'll post it in the channel. But Rosalind, if you have Docker, if you just run experiments like this,
I do have Docker. Yes.
let me perhaps just use the DDPG. Something like that. Sorry, 1 second. If you run something like, okay. If you run something like that in the Slack channel, then it's going to be really fast. You wouldn't have the overhead at all. And the way to achieve that is if you look at my Docker file, it's this shared memory Docker file. Essentially, you do all the regular things, but then before executing any step, first of all, you log in the weight and biases token that was passed through environment variables, set up the XVFB server so that the video can be logged. And lastly, we basically copy everything and then go to the share memory folder and then execute whatever you're going to execute. Does that part kind of make sense?
Yeah, sure.
Yeah. All right.
I get it.
All right. Perfect. And if you want to use it for your experiments, so I would suggest you look something over here. So the bash.py, and the way how it would work is, suppose you compile a test.sh, right, and look something like this. And then what you would do is you would open that. Docker AWS batch, and then you comment out the submit jobs. And then let's say test, you just kind of run it. And then this script over here generates you a bunch of commands that you can just run. So you can just copy these and in your terminal, and then just paste it over there, and it's just gonna work.
Okay.
Yeah, you can also save these to a file or something, but yeah, it's pretty good.
Yeah, I'm really curious on why it doesn't take too much time in the first place.
Yeah, and another thing that you should look. So I assigned one specific CPU to each Docker job. So that's what the CPU set CPU does. So in Docker, there are two different ways. You can limit the number of CPU usage. You can set a CPU share or something like that for the Docker container, but that one is a soft limit, and it's been enforced every 100 milliseconds or something. So it adds extra overhead. However, if you use a CPU set CPU directly, so that will tell the Docker container which CPU it has access to. So it's a much direct access, and there's no throttling, so it's much faster. I mean, I don't know about much faster, but it makes sense, right?
At least the file part makes sense, but by the way, okay, no, it's fine. But it's really weird.
Really weird what?
Or maybe I am just lucky to have a crazy servers.
Maybe. Yeah, maybe I should try to delete this token or something. It's not in the code, but when I do the demo, it shows up. It shouldn't matter that much, but I'll probably change the token anyway.
Did you also notice this slowing down error in TD3?
No, what's the error you're talking about? I'm looking at your screen.
Like TD3 taking too much time.
I don't know what you're referring to. I like how you name it. You don't have to name it unclean.
No, but it's unclean. It was unclean at least when I was doing the work.
I see, I see.
Even humanoid doesn't take that much time.
Yeah, but you have a. Right, right. Yeah, I really don't know. You actually have to profile to see what's going on.
Hmm.
But yeah.
So many projects.
Indeed, indeed.
Uh,
But yeah, that's kind of about what I have. Hold on one second. Be right back. How's working from home?
I am not quarantined yet. So.
Mhm. So, one of the DeepMind intern posted in the reinforcement learning Discord server that feel free to ask any questions on Agent 57 paper.
And
I'm
how?
saying I have a short question. My friend and I were talking about it literally 20 minutes ago. If we decide to reproduce a paper, uh, what is the level of lines of code would it entail? What is the level?
How many years of our life will we have to sacrifice?
Okay, posted the question. Let's see if we have something back. All right, but yeah, that's about it, and very happy. Oh, really interesting. So, is the paper out?
I believe so.
Where is the paper? Is it perhaps in the end of this? I'll read the paper here. I want to see the authors. Does that include this person who is answering questions in Discord?
Hopeful.
The first to achieve the result proposed. And then he just says, haha, that's one question I probably can't answer.
Let me see if I still remember my Discord. Uh,
Most of the components like R2D2 and R&D are open source though. I'm sorry, you were saying?
no.
Okay.
I am currently looking at the discussion in the reinforcement learning Discord.
Yeah, are you in that Discord? Do you want me to send you the server link?
Oh, I am also there.
Oh, okay. Do you see my question over there?
Okay.
Huh?
Yes, I do see it.
Okay, that's pretty funny. But yeah, other than waiting for our researcher at DeepMind respond, is there anything else that you would like to discuss regarding TD3 or anything with respect to the library?
I think I do not have any more questions
Okay.
about it, for now at least.
All right. And by the way, something really heartwarming happened for me. I was really happy. Uh, so I was writing this other library called Port Warden, and it essentially enables you to create encrypted backups for. Do you use any password manager?
Nope.
Oh well, not good for you. But if you decide to
Why?
use, but anyway, check this out. Earnings $3. Someone bought me a cup of coffee. That was pretty cool.
Congratulations.
Yeah, thanks. That was pretty cool.
You already drink the coffee?
I wish I can't go out, but I should probably thank him. I forgot there's a thank you button. Okay, sounds good. Sounds good. Wait, do you know if they outperformed the Mu Zero? Oh, actually,
On some games, on Pitfall, I do not think Mu Zero achieved a significant improvement there. They seem to be the first paper to, not Agent 57, but
wait, I don't understand your sentence. What are you trying to say?
I did not check that paper. I was referring to the Never Give Up one.
Oh, okay, right. I see.
That one made a special emphasis on the Pitfall game.
I see. Yeah, if you look at their performance evaluation, it almost seems that
Why
yeah,
is
Never Give Up is performing really well, And it almost seems to me zero isn't performing that well, actually.
Strangely. Or there is no just enough data, maybe. Although I doubt it. Mu0 is also DeepMind, right?
Yes, it's also DeepMind. It was supposed to be one of the state of the art. Why is it performing so poorly, I suppose? But okay, never mind. But yeah, do you know what a password manager is?
I know.
Okay, well, I'll give you a little demo. But essentially, it's sort of like if you want to, it records your password. Uh, like essentially, what you an example would be, let's say you go to Slack, and then you just kind of create an account. What you would do is you right click over here, and then you enter some sort of username, and then you generate a password, and then you toggle all those things, and your password becomes that, and then you save. And then when you need to log in, you can just click one of those to fill, which, yeah, sign into another workspace. Okay, come on, give me. And you can just, click on one of them, and it'll just fill for you. And
Is that the Warden one?
yeah, that's a bit Warden. I found it very easy to use, and it's open sourced. So that's a really big reason for why I was using it. The reason why it could be open source while still being safe is because it uses end-to-end encryption, meaning that your password is encrypted before they're sent to the cloud. So all the cloud sees is some metadata, and for the most part, the core data is encrypted. So they only see in the cloud, they only see like random letters. It's only decrypted on your local machine, and then you can host it yourself, like what's been suggested over here. And it includes attachments as well. So for example, I use it to store all of my IDs, my medical records, and my tax returns. But basically anything important I put into Bitwarden. It's like if you ask me if I can show you my passport, I just search for passports, and boom, there you go. I just kind of click on it.
That's
Yeah,
that's
it's
cool.
it's very neat, and those attachments are encrypted as well. So everything is very safe, and they're very easy to find. It almost creates this relation, right? It's sometimes it creates this relation that you store files associated with a particular website. So an example might be, I don't know, right? So for example, like Drexel, my university, here, I put my IDs, appointment letters, etc. out over there, and it's important because it's very convenient, because whatever I want to show my ID, I know it's related to Drexel website, and I just click on it, and that's it. I can see all of my important documents associated with this particular university. But yeah,
Do you find yourself in a situation where you have to show your ID online a lot?
my ID, what?
Why do you have to show your ID online?
I don't know. Sometimes, like if you were to file some sort of application, sometimes you need to, I don't know, like there are situations that this happens, I suppose. And the other thing, yeah, so this is my library that does it. So it supports encrypted backup of your vault. So that includes attachments as well. And the official backup solution, they give you a CSV or JSON that is unencrypted. So it's not safe. But my solution gives you, I should probably stop the recording by now, but it gives you, your backups, the encrypted backups that includes all of the attachment as well. The beauty of
Sounds
open
good.
source. But yeah, I'm gonna stop the recording because this has come to an end. But yeah,
You can always edit the video later.
I don't know. I don't like edit videos. It's too much work and too much time to render.
Ooh.
All right, I'll stop it now.